Exercise 3. Let's read the question. In a communication system, each code word consists of 1,000 bits. Due to the noise, each bit may be received in error with probability 0.1. It is assumed bit errors occur independently. Okay, so we can define xi as a random variable which assumes the value 1 if bit I is received without error and 0 otherwise. So xi can assume only two values, and in particular a bit is correctly received with probability 0.9. So xi is a Bernoulli distribution with parameter p equal 0.9. Each code word is made of 1,000 bits. So we can define x as the number of bits in a code word that are received correctly. So this will be the sum from I equal 1 to n of xi, where n is equal to 1,000. Since error correcting codes are used in the system, each code word can be decoded reliably if there are less than or equal to 125 errors in the received code word, otherwise the decoding fails. Find the probability of decoding failure. So, the probability of decoding failure is equal to the probability that x, that is the number of bits received without an error, is lower than 875. Okay, so if exactly 875 bits are received without error, then those received with error will be exactly 125, and therefore the code will be correctly received. However, if x is lower than this number, then there's the code word is not received correctly. So there are two ways of solving this exercise, and for the first one we can compute the exact solution, and the second one will be an approximated solution. So in the exact solution we just realize that x is defined as a sum of the newly distributed IID random variables, and therefore by definition x is a binomial with binomial distribution with parameters 1,000 and 0.9. Great. So we want the probability for x to be lower than 875, and this is just like the sum of the PMF of the binomial distribution evaluated at all the k's from 0 to 874. Okay, and the PMF of a binomial distribution is 1,000 choose k, evaluated at k, 0.9 to the power of k, 0.1 to the power of 1,000 minus k. Great. So, of course, evaluating this probability is quite cumbersome because we have to sum 874 different terms. However, it is possible to evaluate it using RStudio. So in particular, the probability for x to be strictly lower than 875 is equal to the probability of x to be lower or equal to 874. Okay, so this corresponds to the CDF, so it's exactly the CDF of a binomial distribution evaluated at 874, and in R we can evaluate this CDF with the code P binom. Okay, binom is the token for the binomial distribution, evaluated at 874. We have to specify the parameters. So n, which is reported as size in this code, is equal to 1000, and p is probability, so prob 0.9. Okay, right, and this is equal to 0.004532135. Great, and this is the exact, super exact result. However, there's another way to do this, and in particular, if you don't have access to Math Studio, for example, then this is necessarily the way to do it, as we don't have time to evaluate 875 times the binomial distribution. So we can use instead an approximate solution. So we know that x is a sum of IID random variables, and so we don't care that they are Bernoulli distributed. Every time we have the sum of IID random variables with a common mean, that in this case is 0.1, and a common variance, that in this case is 0.9 times 0.1, okay, so 0.09, okay, then we can use the central limit theorem, okay, and we can state that x is approximately normally distributed with mean 1000 times the mean of the single random variable, and variance 1000 the variance of the single random variables. That is a normal distribution with mean 900 and variance 90. Great. So in particular, we want to calculate the probability for x to be lower than 875. That will be approximately equal to, now we can use the normal approximation, so p norm, evaluated at, we'll think about this in a second, so with mean equal 900 and standard deviation equal to the square root of 90. Great. So what is to be put here? So the simple answer would be 875. However, we use the continuity correction because we are calculating an approximation of a discrete distribution. So here we will put 874.5. The result is 0.003594759. Okay, so which is okay, so not identical, of course, to the exact result, but maybe close enough. These two results converges as n tends to infinity. So about the continuity correction, let's have a look at how to use it. I believe you've seen this already. However, we'll do a short summary so you can't go wrong with this. So continuity correction. Okay. We have to apply the continuity correction when we use the normal distribution as an approximation. Approximation. Okay, careful. Of a discrete distribution. Okay, so the most common examples will be the binomial and the Poisson distribution. Okay, so for example, in this case, if we look at the probability for x to be lower or equal than 875, right, without the continuity correction, this will be approximately equal to the probability for a normal, okay, an appropriate normal with the correct mean and the correct standard deviation to be lower or equal to 875. We were tempted to do this before. However, because the normal is a continuous random variable, this is exactly equal to the probability for that same normal to be strictly lower than 875, right? And if we and according to our rule without continuity correction, we would this would be also our approximation to the probability of x to be strictly lower than 875. But if x is strictly lower than 875, then x is basically lower or equal to 874, because x is a discrete distribution. So for this reasoning, which is wrong, we need continuity correction to avoid this. And it's straightforward, I promise, how to apply the continuity correction. So basically, if I have to evaluate with this normal approximation p of x equal n, okay, I will use instead the probability for a normal distribution to be between n minus 0.5 and n plus 0.5. So this is the general idea. And therefore, to be consistent with this idea, the CDF of the discrete distribution x is approximated by the probability for the normal distribution to be lower than n plus 0.5. If instead I'm looking at the probability for x to be strictly lower than n, then this probability will be approximated by the probability of the normal approximation to be lower than n minus 0.5. You can go wrong, right? One event will lead to a probability higher than the other one, and of course we need to be consistent in all cases. Then the last two cases is the probability for x to be higher or equal n will be the probability for a normal distribution to be greater than n minus 0.5, okay? And the probability for x to be strictly higher than n, this should lead to a probability with respect to what we've just written slightly lower, and indeed we will write the probability here of the normal to be higher than n plus 0.5, therefore a probability slightly lower. Okay, so continuity correction, we use it when we're using the normal distribution to approximate a discrete probability. This happens very often when we use the central limit theorem, such as in this case. Nice and easy. Exercise 4. Let's read the question. You have invited 64 guests to a party, so big party after the quarantine. You need to make sandwiches for these guests. You believe that a guest might need 0, 1 or 2 sandwiches with probabilities 1/4, 1/2, and 1/4 respectively. Okay, so let's note this down. So n is equal to 64, and so if we define xi as the number of sandwiches eaten by guest I, okay, then of course xi will be equal to 0 with probability a quarter, 1 with probability a half, and 2 with probability a quarter. Great. You assume that the number of sandwiches each guest needs is independent from other guests. How many sandwiches should you make so that you are 95% sure that there is no shortage? Okay, so we are making inference about the total number of sandwiches needed. The total number of sandwiches needed will be equal, of course, to the sum of all the sandwiches eaten by each guest. So the distribution of the sandwiches eaten by guest I is a categorical distribution, okay? Any finite any probability distribution on a finite state space is called categorical, and it's just it's described and can be described by this curly bracket and the numbers there. However, what is fundamental to note is that the xi are IID. So, we are dealing with a sum of IID random variables, then of course, and the sum n is equal to 64, then of course we can use again the central limit theorem. First of all, we calculate the expected value of xi, which is equal to 0.25 plus 1 times a half plus 2 times a quarter. So like each value that the random variable can assume times its relative probability. And the variance of xi, we can calculate this using the formula the expected value of xi squared minus the expected value of xi squared. Okay, so the expected value squared of xi is just equal to, okay, we didn't calculate the expected value. This is 1, right? So the square of this is still 1. And the expected value of xi squared will be equal to 0 squared times a quarter plus 1 squared times a half plus 2 squared times a quarter. Okay, so this is 1.5, and therefore 1.5 minus 1 is equal to 0.5. So we have the variance of the random variable xi. Let's apply the central limit theorem. The central limit theorem tells us that the sum of these random variables that we defined as x is approximately a normal distribution with mean n times the mean of a single random variable xi and variance n times the variance of xi. Therefore, we have here a normal distribution with mean 64 and variance 32. Great. So let's look back at the question that was asked. So how many sandwiches should you make, okay, so that you are 95% sure that there is no shortage? So basically, we want to find, so if I make Q sandwiches, then the probability that the sandwiches will be enough is equal to the probability that x is lower or equal the number of sandwiches I make. So yes, Q is the number of sandwiches. Great. So to be 95% sure that there is no shortage, what does this mean? That the probability that x, the number of sandwiches needed, is lower or equal the number of sandwiches we have produced has to be equal to 0.95. So this is what this exercise is asking for. How can we calculate this number? So there are two ways, as usual, with the tables or with RStudio. Okay, so with the tables, first we have to standardize this probability. So this will be equal to the probability for x minus 64 over the square root of 32 to be lower or equal than q minus 64 over the square root of 32. Okay, and this has to be equal to 0.95. Okay, so I need to find the q such that the probability that a standard normal distribution as x minus 64 divided by square root of 32 is a normal standard normal, approximately, is lower or equal than q minus 64 over square root of 32 is equal to 0.95. So usually with the tables, you are given with this number here, right? And you use the table searching by row and column to find the probability that Z is lower than that number. This time you have to use the table the other way around, and in particular you have to search for the table for the number closest to 0.95 and then refer to its relative row and column. In particular, well, you will get different results depending on the table that you're using. However, probably with the table you are using, you can find that the probability that Z is lower or equal 1.64, okay? If you use the table, you will see that this is 0.9495, which is very close to 0.95. Okay, so basically we can substitute here 1.64 because we know that the probability for Z to be lower than lower or equal 1.64 is basically 0.95. So once we found that that number should be 1.64, it's very easy to get Q, as Q will be equal to 1.64 times square root of 32 plus 64, okay, which is 73.2772. The alternative way, which is much more straightforward and faster, is to use RStudio. Okay, with RStudio, the command that you have to use to find this number is qnorm. Okay, qnorm is the inverse function of pnorm, right? So qnorm evaluated at 0.95, of course, don't forget to specify the mean and the standard deviation of this normal distribution we are dealing with, okay? So qnorm will give you the number such that the probability that a normal distribution is below that number is exactly 0.95. Okay, so it provides the 95 quantile. This is equal 733047. So this provides the 0.95 quantile of the normal distribution of which we define mean and standard deviation. And if you want to see it graphically, okay, maybe I try and have a straight line. Okay, if you want to see it graphically, basically this is the PDF of a normal distribution with mean 64 and variance 32, and basically the command qnorm returns the value q such that the area below the curve, so below the PDF up to q, is exactly 0.95, and this is defined as the 0.95 percentile. And remember that the quantile function is the inverse of the CDF, the cumulative function, and this is done.